Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Data centers are the backbone of our digital infrastructure. With the rise of artificial intelligence, machine learning, cryptocurrency, 5G, and cybercrime, they face immense pressure to deliver more power, efficiency, and security. Today, I'm speaking with Angad Sandhu, Director of Infrastructure at Google, about how the company keeps the internet running 24/7 while managing its global data centers. Angad leads the design and development of future data centers at Google. Previously, he led the infrastructure engineering at Tesla, overseeing the construction of manufacturing facilities worldwide. He's passionate about renewables, energy storage, distribution, and efficiency, striving for simplicity and effective solutions. Hi, Angad. Thanks for taking the time to talk with me. Let's get started. Will you provide an overview of Google's data centers?
Hey, Dave. Thanks. And thanks for the opportunity. Looking forward to it. Yeah, Google data centers are a vital component of its business. They support the core products and enable our cloud computing platform to deliver a wide range of services to the users worldwide. Our main core products that Google serves is, we have our search, Gmail, YouTube, Maps, and then cloud data centers are serving about 200 countries and regions. We connect this infrastructure globally with about 3.2 million kilometers of terrestrial and subsea fiber. This is about 10 times more than the reach of any next leading cloud provider. Google data centers are designed to handle the immense scale of its core products, processing trillions of search queries, storing billions of emails, pictures, and serving countless hours of video every day. The key focus that we have in our data centers remains on efficiency, security, sustainability, and innovation.
Being an engineer and data centers, every time I turn on CNBC on YouTube TV, by the way, data centers are probably the topic every half hour on the TV, whether it's the need, the scale of them, artificial intelligence demands, the energy requirements for them. It's really, at least from our side of the business, a huge growth area for us, just the number and scale of data centers coming online. I'd probably say every day, it seems like. But data centers face challenges like cooling, security, and scalability. Where does acquiring enough electricity rank among the challenges you have putting data centers online?
Now, that's a great question. Electricity is one of the key enablers for Google data centers, right? In order to make a data center, you need quite a bit of essentials. That includes land, location, permits, cooling, network, and then, of course, we need power to enable these data centers. So electricity is a key component. When we look at sites, power does come up as like one of the main criteria. And when we're selecting these sites, we typically look for what is our available grid capacity in that region, what is the cost of electricity, is that electricity coming from a sustainable source or not, and what is the actual reliability of the energy that's coming for us. It is increasingly becoming challenging to find more and more sites with available power. So that is a challenge, and we are getting creative to get more tools in our portfolio to ensure that we can adapt to whatever is readily available in the market. And, we can dive into some of those details, but whether it's, enabling features within our data centers that can, handle the non-reliability in the grid when it's not available, when all the criteria for power that we're looking for in terms of reliability, cost, and sustainability are not available, we are constantly trying to figure out new ways how to enable more electricity and trying to find creative ways around it.
Yeah, we do a lot of certainly work with connecting the grid to data centers. And as I recall, Loudoun County over in the Virginia area, I think that the commissioners put a moratorium on putting data centers in there because they were it seems like every 5 feet there's a new data center. But what I also see is other states like, say, Mississippi or Georgia or something being really interested in being able to be perhaps other places. Are you seeing the ability to put data centers up in, I'll call it non-traditional, which I assume maybe is traditional areas of, say the U.S.?
I think for a few years, if you go back 2, 3 years back, data centers were unfairly characterized as, energy hogs or water hogs. From a perception perspective, it was like they're considered non-essential, but they're actually very essential to, to the world that exists around us today, right? Like you said, whether you're watching YouTube TV or, you're doing work or we're doing a conference call like this right now, they're key enablers. But I think with AI getting more publicity right now, there is an interest in actually getting more data centers in different areas of the world right now. So there's a lot of interest. Folks want data centers in their countries, whether it's a country like Norway or any European country or a lot of the Asian countries, and even within US. AI is actually making data centers very attractive because people want to host the AI data centers locally in their areas. So the perception that used to be that, hey, data centers are not required or we don't want them in our backyard, that is seeing a little bit of a reversal right now, which is encouraging.
So with digital services and AI technologies growing rapidly, data centers are expected to triple their power needs by 2030. How are you folks at Google ensuring you're going to get enough power, and where do you see you're going to get that power from?
I think there are a few things to unpack in that question, right? There's a lot of concern that we won't have sufficient power, which will be driven by, the need for infinite compute required by, AI, large language models that we have to go and train. The first one is that this assumes that there is going to be a linear this is a linear projection that assumes that compute will grow linearly and does not account for any efficiencies in the models that as they will evolve. That models will run at the same in power consumption as they run today. Also, this linear behavior assumes that there will be no efficiencies or improvements in the chip design. I think both of those, we will probably see some improvements in those. We don't know exactly what those are, but I'm sure as the models mature and get evolved, they will get more efficient. And even the same will go for the chips as well, right? Both the chips and the model will find efficiencies. So this power consumption is not necessarily going to be linear. That is, some of it is my personal view based on, how we have seen technologies evolve in the past, right? So I think that will help.
How far away do you think we are from that? We can speculate we'll get more efficient. I don't know if I've necessarily seen anything that's like right around the corner for efficiency. I think that like the NVIDIA chips, I keep looking at the power just keeps going up and up and up and up. Maybe not even, maybe at a square or something.
Yeah. So the chip power is going up, and I think fundamentally the chips need to run more, more compute. And they also need to be closer to each other. So the rack density is definitely going higher. And that is the key in enabling, large-scale data center. You're absolutely correct. But I think as we will start hitting some physical limitations as the chips get a lot denser, even within the racks. So we will have to find creative ways how to run those models more efficient. And some of these constraints are going to drive innovation. Previously, I think the largest clusters at least for the NVIDIA GPUs, used to be 20,000 chips, 30,000 chips. But now what we're talking normally is like, hey, we should be able to run 100,000 chips or 128,000 chip clusters together, right?
That's amazing.
Yeah. There are improvements in networking that are already happening because we're able to run a lot of these chips together. But I think there'll be surprising developments in this. I can't give you timelines, but I know there will be improvement just driven by the constraints that we have to work within.
Well, speaking of the energy needs, how is the integration of renewable energy sources impacting data centers? They can be intermittent. You can have a lot of power 1 minute and then the wind stops blowing and all of a sudden you don't have as much power. How do you relate them on their reliability, or how do you manage the intermittency of them, I guess, is maybe a better way to state it.
Dave, I'll go back to the previous question, and I want to touch on the second part.
Okay, I'm sorry.
That's okay. The second part I wanted to touch base, and it'll actually tie into this question as well.
Okay.
Would be that, the grid is today, and I'm sure you're very familiar with this, is sized for either our daily peaks or it's sized for our seasonal peaks. Right. So with more electrification coming in future, this is not just going to be true for data centers, but it'll be for everything else that comes along with EV charging and more electrification of our homes. We will have to figure out how do we utilize those valleys that exist in the demand on the grid. And I think that's the key part, which will where we will need to be creative with, both for data centers and everything else that comes along with it. How do we actually utilize those valleys that exist? Because there are seasonal peaks, yes, but then rest of the year, the grid is not necessarily utilized in every part of the country at the same level.
That's a interesting point. I hadn't thought much about it, right? But I've looked at the power requirements when, say, AI is doing some training, right? And it is literally a step function when you say, okay, let's start training the model. You also look at PV and wind, right? We certainly the photovoltaic stuff, the solar panels, right? Get a peak during the middle of the day, and that's actually when we have a valley for at home use and stuff like that. So maybe you end up training data sets and stuff at noon as opposed to anytime you want to when we have an excess amount of energy available at lower prices.
No, totally. I think all of these things combined will drive different solutions. I think what we're also seeing, there's a lot of large scale battery installations that are coming onto the grid right now. I think California has a ton that they're installing. Texas is installing a lot, and both of those states have a very large installed base of renewables. California has one of the largest ones for solar, and Texas has one of the largest installed wind farm base. And Texas is now catching up with California even on solar. I think we've been very spoiled in the sense that we use the grid as our buffer, right? Whenever we need, the energy is available, and whenever we want to throw energy on it, we kind of throw on it. I think as more and more batteries come online, they will actually help with this as well. Now, whether we put the batteries somewhere farther away from a data center or, wherever you need them onto the grid, or you actually put them in your data center so that you can stabilize your load. But the other one also is, can we actually run our models or run our loads at a different time of the day? That flexibility it becomes a financial decision, essentially, whether you want to use your compute that you have spent the money on, rent for 24 hours, or you want to complement that by installing batteries and then be able to utilize your compute at a higher rate.
Yeah, batteries are interesting. I think there's probably a good complement to help when you're running, during a peak load time or something like that for your training or whatever it might be. Usually my concern for batteries, people think of them as there's a natural disaster or something like that, and they're going to be there to help you out. And most people don't realize the batteries are rated in hours, not days or something like that. So for helping with peaking, I can think batteries would really help you guys out. I think for the long-term bulk grid, maybe some peaking application, but certainly not reliable, dispatchable resource. So there's some interesting work going on there. And speaking of that, then, how do you prepare for disaster recovery and business continuity in the event of a major outage? Because as you pointed out, my kids would go crazy if they didn't have access to the internet and searches and all that fun stuff.
Yeah, look, our primary goal is to maintain power and cooling to our data centers at all time, right? In a standard typical data center, if the grid goes out, we have generators, to provide with on-site fuel to provide continuity. That has been the core business for every data center till now, and it still is. But I think I'll go back to this thing of the grid is actually becoming more and more stable in the way I see it over the past few years with more batteries coming online. If you go back 2-3 years ago, California got a lot of bad publicity on
brownouts,
rolling blackouts, right, that they were doing. And that was during the bridge season, right? I think August, September timeframe. When the sun is going down, it's still hot. People are running air conditioning units, and the grid just couldn't handle it because solar power was going down at that point. But over the past 2 years, if you look at the same time frame, the batteries have helped them immensely, right? So I think that is the interesting part. I actually feel grid is going to become more stable than less stable, with a lot of these diverse set of energy sources connected and with batteries and everything. But in the events when we will still run out, like you said, the Texas had the winter freeze a few years ago and took the grid out for a few days. And batteries, obviously, you can reasonably find a 4-hour duration backup. And if you curtail your loads, you can maybe extend that 4 hours to 8 hours or something like that. I actually have a battery backup for my house And, if I shut down the non-essential circuits, I can extend it for, 2 or 3 days to, to get the basics that I need around the house. But from a data center perspective, we are starting to look at, and these are just concepts that we, in the innovation arm of Google Data Centers, constantly think about. We're trying to think of redundancy differently. Instead of building redundancy into each data center, as an example, we think of, can you actually make one redundant data center in a completely different part of the country? So imagine if you have 10 data centers with certain amount of redundancy in them. If you didn't have that redundancy, then your 11th data center is your redundant data center in a completely different location. And could you actually shift all of your compute and needs to that data center if your data center in Texas gets hit, as an example, right? So it's more of like a software and a networking ish problem to solve than less of a power and cooling problem to solve. So those are the kind of things we, as a software company, we kind of lean back on. Are there other things that we can do besides just outside of hardware to think of data centers completely differently? With distributed energy and distributed compute, distributed data centers can help us, with those kind of reliabilities, because certain assets like generators typically just sit there waiting for that 148-hour period when they're going to run and generate for you, right?
Yeah, I don't know what the capital cost is for a data center, but that'd be sort of an interesting concept, is never run a data, or certainly power back on a data center between the 5 and 6 o'clock local time, whatever that peak charge time is and stuff, and just offload the compute to some other data center that's got low power and, like the middle of the night somewhere in some other part of the world. And then you're really thinking you're probably right. You don't need all that extra generation capacity, all those cat diesel sets or whatever, batteries or whatever. It's just cheaper to build a data center somewhere else in the world and just start shifting where the compute happens.
Yeah.
That's cool. That's a really cool. I don't know what the capital costs are on something like that, but it's a really interesting idea.
Yeah, and I think these are all things that we're trying to balance continuously and figure out what is the optimal point, what is the best for environment, what is the best for customers, what is the best for from a capex perspective or from an opex perspective, because you end up designing a lot of infrastructure out in the world for certain design days. Right.
Probably a given technology for that year, right? I can only imagine how you plan out CapEx stuff 5 years out with technology changing so fast and different ways of coming online. And a great design today may be, totally inadequate 2 years from now, or totally obsolete 2 years from now.
Yep, totally.
We talked a lot about AI that you guys support for your customers. How are you all using AI on automation to improve data center operations and efficiency?
So Google actually has already been using AI in our data centers, quite a few years. We basically, accomplished it by taking a lot of the historical data that had been collected by thousands of sensors within the data centers, such as data like temperature, power, pump speed, set points, and so on. And we used it to train and assemble of deep neural networks. And since our objective was to improve the data center energy efficiency, we trained the networks on, average future PUE. PUE is power usage effectiveness, which is defined as the ratio of the total building energy usage to the IT energy usage. We then trained 2 additional ensembles of deep neural networks to predict the future temperature and pressure of these data centers over the next duration, like an hour or so. And we've been using this to actually run our data centers from a cooling perspective. And, the purpose of this predictions was to simulate the recommended actions, from that PUE model that we had, and to ensure that we don't go beyond any operating constraints. That's been happening in a data center for quite a while now, even before anyone else in the world started using AI, right? And at a very basic level, I think if you have a Nest thermostat in your house, you kind of have an AI model in your house already.
I do have one.
Right? So it's just reacting to it. But I think the teams are getting very creative now, looking forward, even more than running the data centers. They're trying to figure out how we can actually design the data centers using AI. So, using all the data that we have on the data centers that we've already built, to feed that into a model and kind of saying, what does the future data center look like, right? So if you can imagine us looking at an SEL relay, let's just say any line protection relay or any feeder protection relay that we have, and we have like, I don't know, thousands of them out in there. And it's like, how do you actually set each one of them with the given parameters available? And can we actually start having models, program them or configure them and so on, right? I think teams are getting very creative with some of those concepts, both on more on the control side, not just how we run the data center. I think that part has been going on for a while, but more of like, how do we actually design our future data centers faster and deploy them based on what our needs are today?
Yeah, we've often thought, some of the things we're kicking around with AI too is, since you have so many data points, if there's an operation on the system, can it analyze? Yeah, that was a everything operated, because you said you had thousands of relays. All of the relays operated as they should, or maybe more importantly, this one, while it did operate correctly, was probably right on the edge of not operating correctly, right? So to get some feedback and looking at data and historical information to make smarter decisions in the future, but being able just to assimilate and analyze large data sets to see if they operated properly or not.
Yeah.
We've been talking about 5G for a long time, and it's getting closer and closer, I think, to all the promises folks have been talking about. How do you all see the rollout of 5G technology impacting data center operations and opportunities associated with 5G?
I think the biggest thing that 5G has probably done is it has increased the content that everyone consumes. I think it may not be very evident so much in the US, but if you go into some of the other countries, India as an example, right? It kind of leapfrogged a lot of the physical fiber infrastructure to people just going to cell phones directly. Now everyone has a 5G cell phone. The latency demands and expectations that they have on things responding initially used to be more forgiving. They're becoming less forgiving now. Right, because you want instant action. So it's forcing us to think of like, how do we meet that expectation for customers in those countries? But then again, the data consumption has just gone up so much. I think that's the main impact that it's having on us more than anything else. We've explored 5G, like using within our data centers, like industrial 5G, for comms and controls and so on. But we kind of get into all kind of security and other issues. I think it's been more attractive in factory environments for like automotive manufacturing, battery manufacturing, where if you want to go deploy tools quickly and get them up and running, I think industrial 5G is pretty attractive there. It's on our radar, but it's not something that we've made a lot of headway into on our side.
What are some of the latest data center design trends or innovations that you all are excited about?
On this one, I think there are quite a few. We've talked about chip density or chip power increasing, that hence increasing the rack density. The problems that we have to go solve there are today, we have a certain amount of space in the racks that is consumed by the power electronics. Right? They take in low voltage AC, they step it down to like 48 volt DC and so on. But as we try and stuff more and more chips into the same rack and increase the rack power electronics wants to grow and eat up the rack space as well. So they're kind of fighting against each other. So I think that what we're looking at, how can we actually take some of those transformation steps out of the racks or out of the data center? So natural thing folks want to go to is a DC distribution system for the data centers. So that's a hot topic of discussion. But instead of just taking, a typical utility voltage from high voltage, stepping it down to medium voltage, and then stepping it down to low voltage AC, and then converting it to DC, we truly want to try and take the medium voltage AC and go directly to low voltage DC, right? And what enables this here is, solid state transformers. I think a few years ago, they were less mature, specifically on the medium voltage AC to DC conversion steps. I think today we're seeing quite a few vendors who have working solutions, right? So we actually have our own microgrid test bed that we're going to try and install a couple of those solutions and see how they work for us. I think if we're actually able to get those into the data centers, that'll free up a lot of physical space.
What voltage would you guys like to see on the DC side, like 48 volts, or what would be the good DC distribution voltage?
Yeah, so 48 volt, it is a good solution that we're using today already. But I think as the power demands go up, it's not good enough. The DC voltage that we truly want to go to is something higher. And I think there's a lot of industry debate and alignment happening on what should be the data center DC voltage standard going forward, whether it's 400 volt DC, 400 volt plus or minus DC, or 800 volt DC. I think it's going to be quite an interesting standard alignment that'll happen between the various hyperscaler as to what should be the future going forward. It's not settled down yet. Those are the discussions that are happening right now.
If you keep it below 50 volts, it's a low voltage system, and there's less UL and all that other certification and things you have to go after.
Totally, and I think that's where if someone is going and servicing the servers. You obviously don't want to expose them to anything more than 48 volt DC. But just on that conversation, like what we're also truly trying to focus on is why do we need to go service those servers ever, right? So we try and follow the principle of like, hey, best maintenance is no maintenance. So we want to try and get to a level where we can make products that we build, we test, we commission, and we deploy, and then we don't have to touch them for a while. We truly want to get to like a lights out data center scenario. So to reduce the OpEx, right? Why should someone go back and touch a server once it's been deployed and it's just running and it runs for the next 5, 6, 7 years till it's reached end full useful life? Then you take it out and then you bring a new one in and you replace it there. But I think that solid state transformers, to answer your original question, is one of the key technologies that we're keeping an eye on. The other one, I think, is we're truly looking at batteries. That is our key focus. I think we're trying to figure out what other benefits we can get out of them besides just power backup. Whether it's power conditioning, grid services, and so on. Can we eliminate additional steps of transformation that happen today? Those are all the things that we're going after.
And it's probably not going to happen tomorrow or next year, but a lot of data center companies are looking at SMRs or some kind of nuclear option. Are you guys headed down that path too, or considering it?
Yeah, Google has actually announced that publicly. I think we've announced a partnership with a company called Kairos. So we are working with companies that are working on SMRs or small modular reactors to figure out can they meet our energy needs in the future or not. But those are not necessarily, obviously they may be next to a data center or close to a data center, but those are not necessarily going in the data center at this point. But they are definitely very attractive to us from the fundamental principle we always follow is the closer you are to the source, the more reliable you are. If you have your energy source closer to the data center, more reliable you will be, right? And if you have any switching happening for a core component, the closer you are to the source, the more reliable you will be. The farther away you are, you tend to have more failure points in between.
Oh, sure.
So it is attractive from that aspect. From you roll your own destiny by having power on site. But then, of course, there are a lot of other challenges in terms of permitting and so on with nuclear.
Well, we're talking about the future. Where do you see the future of data centers in, say, 5, 10, or even 25 years from now?
This is an interesting one, right? So today, when you look at data center, they are giant warehouses with thousands of servers and hundreds and thousands of chips within them. Our hope is that as the racks get more dense and the chips get more efficient, the data center footprint will actually reduce. But the density will go higher where we're not necessarily consuming the same amount of volumetric space that we consume today. We're placing a lot of boxes within boxes. My hope is that at some point we will not need these giant big box shells as data centers. Servers could become something like large battery installation or a transformer that we can directly go place in a field somewhere, and they run on their own for a while. That is something that we, from first principles, I think that's how we should go. There's no reason to have this warehouse kind of an approach for data centers. I think that'll be key because we're constantly being challenged with building faster, and also reducing our embodied carbon footprint. So if we can eliminate a lot of the steel and the concrete that we use for these boxes, that'll definitely be good for the environment. It'll help us go faster, and so on. And the other thing we're also looking at, right, from a first principles perspective, today, if you look at lithium-ion batteries or you look at solar cells, their electric car is like a brute force solution of like 5,000 plus cells, connected together. It's pretty amazing, but it's also archaic in a lot of ways. And when you look at how a chip is powered, it's pretty much connected to the grid, just how a battery cell is connected to the grid in a battery application, right? So you have 1 volt chip, which has been stepped down from, a 12 volt power supply, which has been stepped down from 48 volt power supply, which has been stepped down from a rectifier with 416 volt AC input, and so on. And the same infrastructure is repeated in your energy source, which could be a solar panel, could be a battery cell, and then could be a chip. So you have the same infrastructure repeated 3 times. Can we actually try and eliminate those 3 parallel components and combine them together so that we don't have to do the same amount of copper or parallel paths? So we have the shortest path from energy source to the load consuming, and then you have no transformation steps, right? Like that's really the ideal goal that we would want to get to. And that's like our final vision that we want to get to is like, not have a lot of these parallel conducting paths, and that the shortest path from your energy to your load.
Well, that is really interesting. I like where you're going with that. I just kind of chuckling because every time I hook up a microprocessor now, there's probably 3, 4, or 5 different voltage levels that I need to provide to the thing, right? And some of it have a lot to, is it driving I/O or is it trying to do the fastest compute it can? So it's probably going to be at 6 volts or 8 volts or something as opposed to 3.3 or 5 volts. It's really interesting that, and we're all engineers, so we have to obey by the laws of physics, right? We're not politicians where we can just make stuff. I probably shouldn't say it that way, but politicians just make stuff up, right? We live in the physical world where we have to follow all the, F equals MA.
Yeah. But totally. But I think that's like, I think there's a lot of opportunity, especially with what's coming in our way, to kind of streamline and make things better. I think that just the number of transformation steps that we go through to get to the chip,
it's amazing, isn't it? It's just painful.
Yeah.
Wow, this has been a great conversation. Thanks so much for taking time to talk with us. And you know what? I'd love to have you back on in a year or so to see how things are going. This industry and this area of technology is moving so fast that we'll probably be talking about something completely different a year from now.
Thanks, David, for having me. And I'm sure in 1 year, there'll be a lot of new things that we'll be able to talk about than what we have today, that we haven't even thought about.
All right. I'll see you in a year from now.
All right, Dave. Thank you.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.